So here I have my latest rendition of my simulation attempt to simulate Joseph Newman's motor in LT Spice using a transformer with reverse or swapped polarity as my interface between his coil and his coil here, L1 and R1, and the rotating bar magnet represented by L2 and R2, supplied by a third energy source, V3, 1 gigavolt. And that is because I lowered the coupling coefficient to 0.5 between the two inductors. And that means there's less efficiency of energy transfer. Because constant 314 was assuming that this was supposed to be a transformer, and it's not. It's just a transformer being used to emulate a rotating bar magnet, on the inside of a coil of wire. So in order to accommodate his suggestion of going to 0.5 coupling coefficient, previously version 7 had 0.99, I had to raise the inductance and the resistance of L1 and R1, raise the capacitance of C1, and raise the voltage of V3 in order to get a negative, predominantly negative amperage on the battery pack, which also created a negative wattage on the combined energy going in, both the volts and the current, the watts, as well as it turned out to be a negative wattage on the coil. And so I decided to list them here. I learned about it, I was trying to do my own averaging by exporting the data points and then using a spreadsheet, but I don't know how to use a spreadsheet to get an average or to do anything. I've never used spreadsheets before. Well, it turns out LT-Spice has a faculty within itself of giving you the average, also the RMS of a wave plot. And so I just decided to put it out here in plain view. So the average amperage here among this waveform is negative 3¼ amps. And the average wattage going in, measured here at this point, voltage in, along with the current here on the battery pack, the combination creates a wattage, and the average wattage is negative 974 watts. So close to negative a kilowatt, showing that, again, energy wants to go back into the batteries. And then the average wattage on the coil is negative 25½ kilowatts. So everything about the system in the circuit is negative due to the influx of energy coming in from the rotating bar magnet, even though it's a loose coupling of 0.5. Now, I didn't want to push my luck. It's not a question of luck. Push the eccentricity of this, input, 1 gigavolt, that's pretty big, by going down to 0.01. He said, constant 314 said it should be somewhere between 0.01 and 0.5 if it's going to be a loose coupling and not a transformer. Well, I went for the higher of the two figures. I didn't do the average. It was difficult enough, and I had to fine-tune this capacitor just right. It became a very narrow window. Not too high, not too low, lest I lose this negative predominant amperage. And I had to also achieve a voltage on the coil of close to 667 volts, and I achieved a high of 680 and a low of 280. Because that's what Dr. Hastings said. Well, that means the average is going to be off. The average is probably somewhere around 480, so this is actually a little low, which means I would have to back off on this capacitor and lower it maybe to 2.2 or something farads. But I didn't bother. I got a very interesting waveform here, though. It started to iron out, so it's less bumpy, less complex, and now it's just veering to the left, which means that the self-shorting of the coil is making it drop, I guess, in addition to the fact that the duty cycle is only 50%. So I think what happened here is we got an inversion, because normally The duty cycle would be a square wave here for 10 milliseconds and then drop. But instead we got it rising because it's going in the negative. See? So the whole thing became flipped. And then we get a piece of the sine wave here instead of it flatlining. So it's kind of fascinating, you know? It's kind of weird. But that's the average on the total wattage, the total power coming in is negative kilowatt. A negative 1 kilowatt, which is not bad. You know, everything else is quite excessive, obviously. The wattage coming in from the rotating bar magnet, it gave up. Beyond terawatts, it gave up, so I don't know what that is. 2.4 to the 17 times 10 to the 17. I mean, whoa, that's a lot. 480 megaamps, 1.4 versus negative 1 gigavolts. That's a lot of energy, but I had to overcome the loose coupling of 0.5. That's why I had to boost all that, and also boost the capacitor too, and boost the I had to boost the inductance and the resistance on the coil. So now it's actually closer now to what Newman's motor is, because Newman's motor, you know, this particular, originally it was 16 kilohenries and 50 kiloohms on the coil. And I had to drop it when the coupling coefficient was 0.99. I had to severely drop it to 1 kilohenry and 1 kiloohm. And I think the voltage coming in through the rotating magnetic field of the bar magnet was something like 1 megavolt or something like that, or 100 megavolts. I can't remember. Actually, why don't we go find out rather than think about it. 500 kilovolts. So this was the previous version 7. But you know, see, and look, the waveform was entirely different. And I didn't plot the averages, but you can see everything is shaped different, and this combined waveform of the volts out and the current out on the coil is a slightly more complex waveform. It's not so smooth. But the values coming in are a little lower. You know, it's gigawatts instead of beyond gigawatts. But I got the voltage pretty good, 770, a little high. So actually this new way is a little closer to the mark, because it's 680 volts on the coil, which is very close to 667. So I like this latest version, actually. Now, of course, this is just a ballpark to give you a rough idea of what's going on, because this is a simulation, right? It's not the real deal. But I managed to satisfy a few of the most important criteria, namely negative amps on the battery pack and 667 volts on the coil, with 300 volts coming in from the battery pack, and what else? Of course, you know, this other business here, you know. And all of this data pointing to the fact that all of the gain is provided by the permanent magnet rotor. It's not coming from the ether, it's not coming from the copper atoms. True, you have to have a lot of copper here to pick up the rotating magnetic field and process it efficiently, and not let it go to waste. Because you have to be able to get the amps on the battery pack to go negative. Not a lot, you know, the average is just 3¼ amps, not a lot, but it has to happen to show that you've got a gain on the coil, seemingly from nowhere. If you don't take the rotating bar magnet into account, you know, it's creating an AC field, just like an electric generator, sufficient to recharge the batteries, because Dr. Hastings said there was a slight negative amperage on the batteries, indicating it can't come from the batteries to go negative. It must be coming from the coil. Well, that's half the story. It's coming from the rotating bar magnet, being transferred to the coil, and hence then to the battery pack. So the copper the mass of copper in the coil does have to be large because the coil is acting as an antenna, and the rotating bar magnet, a receiving antenna, and the rotating bar magnet is acting as a transmitting antenna of sorts. It's, so let's see. Now, I think I might have figured out what the swapped polarity means. It has to do with the simulation. So the coil is wound one way, let's say it's clockwise, and so the electromagnet that the bar magnet is being simulated here is wound the opposite way, counterclockwise. That's what it means. Let's see what else. I think that covers everything. So I'm very happy with it, and it's not getting any worse, I'm still making the changes that I can make that Constant 314 suggests. He thinks it's odd that on my LT Spice, I cannot internalize this resistor as a series resistance on the coil. And if I can't do that, there's no point to internalize the capacitance. Well, I'm not supposed to internalize the capacitance. The capacitance is an exterior set of capacitors. This is the way Joseph Newman set it up. So I'm not surprised that I have to take out the resistor and it doesn't work, because karmically there's really no other way but to remove the capacitor and have it on the outside, connected in parallel with the coil. Now, what that does to the waveform is that this capacitor acts as a decoupling capacitor to a limited degree, removing some of the AC influence from the coil, but not all of it. That's why I say it's a narrow window. You have to get just in the right place so that you remove some. So here we got a square wave, but not all of it. Now here we got a half of a sine wave. And that's kind of like a diode would do that, But somebody suggested, oh, we should use a diode, single diode rectification. No, you don't. It doesn't work. Not in this situation. It's not going to work. It's going to, it's funny. They're going with what they're taught, some of these newbies, Oh, it'll work for everything. No, it doesn't work for everything. Sometimes the things you're taught in school doesn't work for everything. In fact, just about you can take it as a given that what you're taught in school is not going to work all the time. It only works for certain things, and it doesn't work for everything. So you have to learn a whole new set of skills when you're dealing with a seemingly over-unity situation. But I'm given to suspect, and I've been suspecting this for some months since I started simulating, that if we think it's over unity, if we think it's free energy, then we simply do not fully understand the circuit, where the energy is coming from. So we claim, oh, it's the intelligence. I like to claim, oh, it's the intelligence of the circuit. Well, that's pretty vague. It's about as vague as claiming the ether or the zero-point vacuum field. They're all vague. And it shows that we don't fully understand the circuit. And I'm not surprised, because these all seeming over unity circuits are very sophisticated. They are not flashlight circuits. They are highly sophisticated in what they do. Even though Newman's motor looks simple, it's, what's the word I'm trying to think of? We're being deluded, into thinking that it's simple. It is simple, but it's very sophisticated. You have to be very skillful in how you put it together, because you don't just throw the stuff together and it'll automatically work. That's a flashlight circuit. You throw together a resistor in the form of a light bulb, a battery and a switch and some wire, and you've got yourself a flashlight circuit, and it doesn't take any skill. Any child could put that together and make it work. But to do something that looks like over unity takes a good deal of skill, let me tell you. It takes hours and hours, days, weeks, months, depending on what you're working on. It can take a very long time. And I say months, actually, not for a specific circuit. A specific circuit might take me a week, at the most, or a couple of weeks in this case. But to get the general feel of how to do something like this does take a long time. It's a general skill that does not come overnight, because we're not accustomed to think this way. To think that it can be done, and not just to think, not just to dream, but to actually be able to pull it off in the world of the simulator, which in itself is easier than the real world. So as difficult as it has been for me, it's even harder to actualize this, because it's not going to be exactly like this, you know. But Newman tells us how to build it. And that's why I use a shortcut link. A shortcut link to, what is it? is.gd/ Newman chap numeral 6. Because after you get past Dr. Hastings in chapter 6, I added other pages out of the 8th edition that Newman gives you pointers on how to build it. He talks about the theory in the early chapters of the book, but finally he gets to the actual hints. Oh, you got to use a capacitor. It's a good idea. He didn't say that in the opening chapters of the book, that you have to use a capacitor. And that's why I always wondered, well, is the long stretch of wire acting like a capacitor because there's so much surface area there? No. Yeah, but it doesn't count because I calculated it only amounts to something like 200 microfarads, which doesn't amount to anything. It doesn't do anything. Yet I had this feeling that there was a capacitance involved, and lo and behold, he does say it's a good idea to put a capacitor in parallel with the coil. So my heart was telling me the truth, but my intellect was going, yeah, but where? I don't see it. Show me. I don't see it. Well, Newman showed me. And it was tucked away in one of the appendices of his book. I think it was Appendix 7, maybe, I don't know, of his 8th edition. Appendix to the 7th edition, I believe. I'm not sure. Anyway, I just kind of stumbled across the pages. I just had to go page by page and just leaf through page by page and see if I could find anything. Because he gets he hops around in those appendices. He doesn't, thematically develop his ideas like he did in the chapters. Even the chapters towards the end hop around. It's only the early chapters that are very thematically chronological in the sense that you read the first, just like he says, you read the first, you read the second, and if it's too lame for you, it's, old news for you, then you just skip through it very rapidly, scan through it very rapidly, page by page. Oh, I don't need to read this, I don't need to read this, I know this, until you get to something you've never heard of before, and then, okay, now it's time to read, instead of just hopping along like a rabbit. Let's see what else. I think that's all I can think of. So I wouldn't expect that the rotating bar magnet actually has a gigavolt, but who knows, It's probably something similar. So that's why I don't worry about the details of how I produce these waves. The important thing to me was no longer how I create them, but just that I create them. And the fact that the inductance on the coil and its resistance is very close to what Dr. Hastings in Chapter 6 was measuring 16 kilohenries and 50 kiloohms on that coil. And it was just a measly little 145-pound coil with a 14-pound bar magnet. A real tabletop model, but and giving 667 volts on the coil. I had to infer because Dr. Hastings didn't say that. He said 10 watts and out, and I think it was 5 milliamps. So I never was able to achieve 5 milliamps, 150 kiloamps. No, I don't think so. But, some things had to go. They had to give. They had to make way for my obsession of getting the right voltage, because it's all about voltage. The coil operates on the basis of voltage. You raise the voltage, then you automatically raise the RPM if you raise the voltage on the coil. And that was the other thing. I had to limit myself to the RPM, which was, I think it was 136 RPM. So I just tweaked it so that it would be a 20 millisecond duty cycle. Taking into account he had 20 divisions on his commutator, so each revolution now we multiply by a factor of 20. So it came out to be a little over 20 millisecond duty cycle, and I just averaged it down to 20, a whole number, to make everything easy for myself, because I had a simulator. I don't want to make this too difficult. But so that's pretty close. So 20 milliseconds well, let's see. Where's my 20 milliseconds? So that's 0.02 flipped. Oh yeah, 50 cycles per second. And so that's what I put, 50 hertz, on the rotating bar magnet. That it's rotating at a rate of 40 cycles per second. Because I have to match the sine waves of the rotating field of the bar magnet with the square wave duty cycle, the whole duty cycle, the 100% of that's coming in, you know, getting chopped up here and chopped up here, a little modified, but mostly chopped here. It's coming in DC from the battery pack. It's getting chopped up by this switch, S1, into a 20 millisecond duty cycle. You know, half of that, 10 milliseconds on. See, that's 10 milliseconds on, and then the full length of the duty cycle of 20. So that means it follows by 10 milliseconds off. And then I make the self-shorting of 4 milliseconds, the last 4 milliseconds of that 20 millisecond duty cycle. So from 16 to 20 is the self-short of the coil. And then I have to start collecting the data on this simulation at the 100-second mark, and then just go for 200 milliseconds, which is what I did here. But this bar doesn't show you that this does not start at 0 seconds when from a dead cold start. It starts from 100 seconds because there's a lot of warm-up in the amps on the coil. And I believe somewhere else the volts have to drop here coming in at voltage in. No, actually they're constant at 300 volts, so DC. So something drops. I guess it's the current, right. I think it's the current coming in from the battery pack. Actually, no, it rises while the current or the volts on the coil drops. I forget which one. And so I had to pick a place within the running period of the simulation at which everything evens out very nicely and you don't see anything rising or falling. So in actuality, this is not what you see as it starts up. In fact, I have a graphic for that. If I can find it. Here it is. And this is at the very beginning. So we have a 400 millisecond frame of reference. It starts at a cold start, and as you can see, the volts coming out measured here. So the volts on the coil is rising, and the volts coming in are dropping. No, excuse me, the current. The current coming in from the battery pack is dropping, and the volts on the coil is rising. And the other thing is that it changes. Some of these waves tighten up as time progresses. So that's the other thing that I discovered. So you have to advance ahead. And in my case, I advanced ahead, is this the right one? 100 seconds in order to get a nice stable sine wave that's not rising and falling, or other kinds of wave, you know, a complex wave that's not rising or falling. So, you know, those are the kinds of things you might overlook if you don't know what to look for, you know, like this trans statement over here, this dot trans statement. Then you would see, oh, he's not starting at 0. I wonder why. Well, because it takes time for the Newman's motor to warm up to its cruising speed. So it slowly increases its RPM because it's accumulating voltage on the coil. And isn't that what I just said? The voltage is accumulating. It's going up. See, this is exactly what Newman said. So I know I'm doing something right, or else I wouldn't get these kinds of responses. So the exact numbers may be a little off, you know, but overall I'm doing pretty good. So the voltage goes up on the coil as the thing speeds up, but the current comes down. You know, the current that's being drained from the batteries is going down, but it's going to be high in the beginning. So don't be put off. Oh, it's not the way Newman's. Vinny, you're lying to us. No, I'm not. You got to do two different versions. One at a cold start, and then one after a certain length of time. And what you do is you do it for a long period of time, and then you see where everything peaks, where it plateaus, I should say, where the rise and the fall plateau, and then that's your cutoff. And then that's, or the cutoff at which you begin. If you want to look at this from a stable standpoint, you begin your traces at that point where it begins to plateau. And then you've got a stable system, and then you can see, oh yeah, I've got 680 volts on the coil, but you didn't have that in the beginning. You had 0 volts on the coil when it first started, you know. This is 0 it starts at, and it takes its sweet time to rise. Now, whether or not it takes 100 seconds in the real world is another story, and no, I don't think so, because in the documentary, if you go online at Amazon, somebody did a documentary of Newman just, well, they interviewed him, you know, just before he died, and then they put it together. The guy, the director or producer, spent like over a decade putting together all the data, all the film clips, you know, acquiring all the film clips. And then when they finally got around to interviewing him, it was just before he died, and then they put it together and made it public after he died. So what I'm trying to say is that one of the film clips they showed, they went to his, I want to say shack, his lab behind his house. This was before he got ruined, you know. He was still living, I guess it's Lucedale, what is it, Mississippi? You know, he still had his wife with him and whatnot. He hadn't been ruined by the patent office yet. And he started up the motor. It was a huge one. I think it was 6,000-pound coil or something. I don't know. It was huge. And they said, okay, now we have to go away and wait. And they went into the house. You know, maybe they had tea or something. But it must have taken a long time, several minutes, maybe an hour or two, you know. And then when they came back, it was really hustling. That rotation, it showed on the film clip, it was really hustling. By comparison to the speed at first, when he, you know, started the turning of the bar magnet by hand, you know, he had to push it several times to get it going. And then once he got it going at his arm pushing speed, he couldn't add any more speed to it, and that's when it was time to walk away and, you know, hang out in the house to wait for this thing to speed up, because it's slowly amassing voltage while the amps on the battery is dropping. But it's slowly amassing voltage on the coil as the RPMs accelerate on the coil. Or, excuse me, accelerate on the bar magnet, the rotating bar magnet. In this case, though, I have an advantage because I force the rotation of the bar magnet at 50 cycles right away. So I don't give it a hand push. So this is actually not an accurate simulation, now that I think of it, because it's anchored to 50 cycles per second throughout the simulation, and yet we still find voltage accumulating on the coil. But in real life, you wouldn't get that. You would start off with 0 RPM, or 0 cycles per second, and it would slowly rise along with the voltage on the coil. The RPM of the bar magnet would rise along with the voltage on the coil. So, you know, there's some problems with the accuracy of this simulation. I'm not sure how to change. I'm not sure how to tie the RPM to the voltage, the coil voltage, the RPM of the bar magnet. I don't know how to do that. I'm sure there is a way, and I'm sure it'll make things more complicated, but it'll make it more realistic. And then maybe I won't have to have these excessive values, see? Megawatts, kiloamps, you know. That's really bizarre. And that might be where my problem is, now that I think of it. So I'll have to ask someone, how do I do that? How do I tie the cycles of the sine wave production to the voltage on the coil and give it just a kickstart, which is probably, if I had to take a guess how quickly a hand can turn a heavy bar magnet, you know, it was pretty heavy. And the guy's strong. He's a weightlifter, you know, a bodybuilder. I couldn't do what he did. But to get a starting speed, a guess estimate, I have to guess that it might be 1 cycle per second. Maybe 2 cycles per second, but not much more than that. Might be more, 3 or 4. Let's say 4 tops, 4 cycles per second. Let's round off to 5. So somehow this thing has to start at 5, yet be tied to the voltage on the coil such that this value here rises to its optimum speed, which may not be 50, you know? It could be something else. But then I bet these values will be more reasonable, maybe. Or there'll be something else. Who knows, you know? So I'll have to ask how to do that. So this thing continues to progress, and only because it's a cooperative venture between my critics and myself. And if they give me something constructive that I can work with, so be it. I can assimilate it and integrate it into the circuit and make the circuit evolve into a better simulation. But if it's not constructive criticism, if it's just an opinion without data, then for me to go on, then I have nothing to do about it. You know, it's none of my business. Oh, one of the other things Constant 314 said, this is not realistic for a simulator to have 1 femtosecond as your rise and fall time of the square waves. So he said 1 microsecond would be better, and that's what I ended up doing. I changed it back to 1 microsecond. Originally it was, and I thought, well, I'll be so smart. I'll make a crisp, clean, 1 femtosecond rise and fall time of the square waves that are getting chopped up here, and getting chopped up here as well. And he said, no, that's not right. So, okay, fine. I'll go back to 1 microsecond. So, I take his advice because he gives me constructive hints of what I should do. And all I have to do is follow through. But if all I get is an opinion saying, oh, that's not going to work, it's not practical, this, that, and the other thing, those are opinions. That's not constructive criticism. And that's what I need is constructive criticism if together we're going to make improvements on this simulation to make it more realistic, to help inspire people to take it seriously, to take Newman seriously. That's the whole point of these simulations, is to not discredit him, not badmouth him, not sweep him aside, not trivialize him, because I know he did produce something useful. It just has limited use. It's a torque-oriented device of kinetic motion. It's not going to produce electricity like some people think. Oh, electricity, let's feed what comes out and feed it back in. No, and make it a perpetual motion machine. Oh, it doesn't work. Yeah, because you can't do that on his machine. You can't. Now, maybe you can feed the mechanical motion back in, but you don't need to. The volts on the coil is taking care of that. So, I mean, it's already, actually, yeah, it's already a perpetual motion machine, but it's a mechanical self-perpetuating machine, not electrical. The electrical is just the side benefit. It's the consequence of the rotating bar magnet working in conjunction with the coil and the commutator. It's really the whole thing working together. It's not like you can make a definitive pathway from the output and wire it back into the input, even if you just take the mechanical motion into account alone, but you can't, because it's both the mechanical and the electrical working together. So this is not a Bessemer wheel, by no means. And it's not an electrical device that's a perpetual motion machine either. It's an integration of the kinetic and the electrical working together to create what appears to be a self-runner, a perpetual motion machine. So you see that it's very sophisticated, even though in its what's the word I can't think of? It's misleading. It's misleading to think that, oh, it's a simple machine, I can do that. Oh, it doesn't work. Oh, the guy's a fraud. Yeah, because it's not, it's disarmingly simple looking, But in actuality, it's highly sophisticated, despite its appearance of being simple because it has so few parts to it. But hey, you can't ignore the largesse of the coil and the largesse of the bar magnet. You can't ignore that. And you can't ignore how he designed his commutator. These are very important points. And you can't overlook the capacitor to put across the coil to suppress arcing on the commutator. You can't overlook that. These are like the important points you have to pay attention to. And you can't use a battery, or you don't need to use a battery that has a tremendous amount of amp hours, because you don't need it. Why go to waste your money on a 100 amp hour battery when you don't need it? A little transistor battery is fine. You could use a 1.5 volt battery. It's fine. You just need a lot of them in series to give a lot of volts, because I'm only doubling the voltage you know, between the voltage in and the voltage out, you know. This is not a huge magnification of voltage. It's just a doubling circuit for doubling voltage in that sense. Okay, what else? And of course, you're getting negative amps coming back on the batteries, so hey, something's happening, you know. Well, yeah, with negative. I wonder what the negative volts, what the volts are, the average volts. Let's go find out. Let's find out what the average. So this is. I'm going to show you how it's done. Okay, you got to wait a bit because it takes a while to simulate it. It's a little bit of a complicated circuit. It takes a little while. All right, now what you do is you hit Control and you left click. So I depress and I click. Okay, the average is 480 volts, 481. So it's not negative. The volts are positive on that coil. It's the amps on the coil that's negative. So let's go find out what the amps are. The average is a negative 100 amps. That's the average amps on the coil is negative 100 amps. And that's why we can get an average of a negative kilowatt average on the coil because of those negative 100 amps on the coil, which shows that the rotating bar magnet is overpowering the amps that would have developed on the coil coming from the battery would have been positive. Instead, it's negative. So it shows that the actual amount of amps being delivered to the coil from the rotating bar magnet is more than 100. Okay? More than 100 negative amps. Because that's just the net amps on the coil. After you've subtracted the lesser quantity of amps coming from the battery pack from the amount of amps coming from the rotating bar magnet, and what you're left over is 100 negative amps on the coil. So what is the actual amount of amps being delivered? Well, let's see. If we take L2, where's L2? Here it is, up here. And then we take its average. We're getting negative 2.7 mega amps being delivered, or being sent, I should say, to the coil. But the coil doesn't pick all of it up because there's a very poor coupling coefficient between the two electromagnetic fields of only 0.5. So I don't know how to interpret that. Does that mean the actual amount of amps is half? Yeah, let's assume that. So let's go back. What was it again? So let's cut that in half, and so that becomes. And if we, yeah, if we cut it in half, that would be 3.525 is what's 3.5 and 2.5? 6. 1.6 mega amps negative is being maybe absorbed by the coil. But see, that means that there's a tremendous amount of amps coming out of the battery pack. Well, let's go look. Where would that be? I don't have it here, do I? Well, we know it's 300 volts in. So if we take this, right, if we take 1 kiloamp negative and divide by 300 volts, let's see, 1,000 divided by 300. Oh, that's like 30 amps. No, it's 3 amps. Right, 3 amps. I have that already. Oh, but that's the net amps. Huh? Wait a minute. That doesn't tell me how much amps the battery was putting out before it was neutralized. No, it doesn't. I don't know. Yeah, I don't know how to, if I can, what's the word? You know, derive. I don't know how to derive from the information available how much amps was coming out of the battery pack versus how much was coming into the coil to create the net result. Because it could be any pair opposites, that the overall result will end up being the same. It could be any pair of factors, but oh, so that's a solution in two unknowns, and that's why I can't do it in my head. I have to do it on paper. That's what it looks like. It looks like a solution to a polynomial in two unknowns to try to figure out how much amps is coming out of the battery, how much amps is being absorbed by the coil, such that the net result is negative 3¼ amps average on the battery pack. Yeah, I don't know. I'd have to think about that, but if I thought it was worth my while. If, feel like I have nothing else better to do a little math. Yeah, in two unknowns, that's a little more difficult, and I never could do that very well, so I don't remember. I'd have to look it up. I'm sure it's online. They tell you how to do it. Just everything's online. Almost, not everything. Certainly not this. Until now. Now it is, because I've posted it on is.g/Newman chap 6, numeral 6, and also on Wikipedia Commons. Well, because I use it on my talk page. You go to Wikipedia user Vinyasi talk, and that brings up my talk page, and that's where Constant 314 has moved the discussion to, because he feels it has to be contained, because this is definitely over unity. This is, fringe. No, this is definitely fringe, because Wikipedia editors cannot come to a consensus to all agree with me. It's a party of one. I'm agreeing with myself, and that's it. So they all disagree with me, and so for that reason they have to contain me, because they don't agree with me. We don't have a consensus. So the whole point of this simulation is to make it more believable, but it's still not entirely believable. So I'm going to have to work on this and get rid of this 50 cycles set value to the rotating bar magnet, and then maybe it'll start looking realistic, even to me. But it's getting there. By little baby steps, it's getting there, baby step by baby step. So I'm going to ask Constant for some hints, some clues. How would he modify this circuit in its current incarnation, version 8, to function in the way that I've described? And then it'll probably be more realistic in how it behaves. Anyway, I think I've said enough. Catch you later. If I can turn this off.